Guys, so keep solving our physics subject GRE. So 61. Basically, you have an electromagnetic wave on a plane wave propagating in vacuum has the electric field, and normally inserted on perfect conductor and x equals 0. Okay, so immediately to the left of the conductor, the total electric field E and the total magnetic is given for following, which will follow. Okay, so for the conductor, basically, you need to remember the electric field, the boundary condition, and for the conductor, the tangential component must be continuous. Okay, so what we have is the tangential component must be continuous, and the normal component changes just the free charge. Okay, so the plane will traveling in the x directions because this is x equals 0, right? So and the e can be viewed as a z directions. Okay, so we can have this. Okay, and so there's no component perpendicular to the conductor at the boundary. So the first boundary condition implies the free charge. Okay, so from this one, that we know that this is x equals 0, right? So that means let me plot. This is more easy. So this is x equals 0, and then your wave is your electric field is in these directions. Okay, so the total electric field and total electric field. Basically, the condition says that the tangential component is 0. So the transmitted wave is, and so in a perfect conductor in here, then because this is perfect conductor, so electric field must be 0. Which tell you that from left hand side the electric field also must be 0. So total electric field from left hand side must be 0. So the answer must be A or C. However, suppose this is your electric field and this is normal perfect conductors, and this is original wave. Then this is your magnetic field, and since your electric field must be cancelled, and this is your reflection wave, and use the right hand rule, you can see that this is the magnetic field, right? So you can see the magnetic field has the same directions. So the total left magnetic field must be non-zero. So the answer is C. Okay, 62. You have non-relativistic particle with charge twice then electrons move through the uniform magnetic field. Okay, the field has this strange strange magnetic field called pi over 4 and it's perpendicular to the velocity. So basically the QVB just equals mv squared divided by r, or m omega r, and then this v is just omega r. So from here we can get let me see. I could get a cyclotron frequency. You can delete one r, delete one omega. We get omega is q. Okay, let me see. So QVB just m omega square r. So this is q omega rb m omega square r. So we can cancel 1b. Okay, so we have this formula, omega QB divided by m. So we can just plug a number. Okay, and then remember that omega is 2 pi f. So what you ask is the cyclotron, what is the particle mass? So we can solve the particle mass by QB divided by 2 pi f. Plug all the number in, then we can get the answer is A. We can get the answer is A. Okay. Since we know Q, we know B, and we also know F, then it's easy. Okay, 63, the distributions by I of lambda of this, and if the Wien displacement law constant. Okay, so Wien displacement law, let me write down. The Wien's displacement tell you that lambda max times t is close to 2.9 times 10 to the negative 3. So lambda max is what? It's close to 2, right? 2 microns. So you can solve the temperature. Just use 2.9 times 10 to the negative 3 divided by 2 microns. Okay, so the answer is close to this. Okay, so 100,000, 100k. Oh, this is 1,500k. Okay, so answer is D. 64. Someone asked about electromagnetic wave radiated per minute provides a mean to probe a spectral physics universe, which is not correct. So lights are in infrared visible ultraviolet region spectrum with your primary nuclear structure of the sample. Okay, so actually this is the answer, but we can just leave it because the nuclear structure is much smaller, right? So usually you need like X-ray or gamma. You need X-rays or the gamma ray to detect the nuclear structure of the sample. And the B is okay, and the C evolution situation can be used to determine B. The C is also okay. D is spectral analysis can be used to identify the composition of class and dot. This is also so B, C, D are very reasonable answer. E is band structs are due to molecules. This is also known because molecules you have many mixed energy spectrums, so you can see the band. So the answer is A. Okay, so 65. Basically, you already have formula. Somebody asks you about high temperature, right? So this is not physics, right? This is the mathematics. Right? All you need to know is do the high temperature expansion for this is as t goes to infinity. Okay, so just use Taylor expansion. So this term I preserve, and this one 60. So I use this, right? This is 1 plus x, so I get 1 plus this, and this is also 1 plus this. So what we got is h nu squared ka squared t squared. Okay, not k squared. Okay, so we can compute it. So 3k Na times this. This is the first order, and okay. Okay, so when t goes to infinity, then this term can be eliminated. So the first, this is the zeroth order. Basically, is a constant. Okay, so the answer is D. So this is not physics, right? Just ask you about the high temperature, the Taylor expansion for the exponential function. Okay, and so 66. Basically, you have a sample of radical neutralized. Basically, you have gamma interaction, gamma emission, beta emission, and you know half of time, and for gamma and the beta asking about total half of time. So you know half of time of the gamma, then this is the equation you have, right? This is the differential equation, and this half means half time, and 24 is here. So you also have this. Okay. And then your total spectrum, your total dt or dr divided by dt, your total reaction is you can add them then together, right? So the direct computation, just this. Okay, and we want then to be this, right? Just same as some r. So this is this tau is the total half time. Okay, so basically you can solve it. And okay, so if you solve it, then you will get this. Okay, I suggest that maybe you can try to remember this answer. So tau is just 24 times 36 divided by 60. Okay, so it's 14.4. The answer is D. I suggest that you can remember. I suggest that you can remember this answer. But basically, once you write down a differential equation for then the rest is just very easy. Just follow directly. Oh, okay. So 67. You have this nucleus has the binding energy about 76 million per neutron if a nucleus were to fission into two equal fragments. Each will have a kinetic energy of just 100. It can be calculate what? Okay. Oh. Okay, so the initial binding energy is this. Right, since we have a lot, for each one we have this one. Okay, so we can close to this. Then we just leave it. Okay, and the final binding energy is UF. Basically is okay, so the final binding energy, actually we don't know, right? But at least we know that suppose for the final binding energy, each neutron will have x MeV per neutron. So total we will have this. Okay, so we know that UF minus UI is 200 because this is the kinetic energy. Okay, so it tells us that we can solve we have to get 240 x minus 7.6 close to 200. So x is close to 8.5. So we can get the answer must be E. The neutron near 120 must be bounded about 8.5 MeV per neutron. So answer is E. The answer is E. Basically, the ABCD that basically you do not know. Basically CDE. Basically, once you see this type of question, you know that CDE are similar, so you can know that the answer. You can guess the answer must be one of them. Let me see. Okay, I think the video is enough for today, and I will see you guys in the next video.